If you want to take your mic off for a minute. And ask a question, feel free to do that. Today we're going to talk about constrained optimization. Let me know if you can't see anything online or if you can't see it very clearly. What we want to do is extend our capabilities. The last two times what we were talking about first was finding local maxima and minima. Right? If you have a mountain function like you see pictured here, suppose I want to find the tip top of the mountain, this absolute maximum. That's my cursor now. Trouble with this program. Suppose you want to find the top of the mountain or the bottom of a valley. That's a local maximum or minimum. Right? Here's the curve for the picture online. If you want to find the very tip top of the mountain or the bottom of a valley. Then the second case was, suppose you want to find the maximum or minimum of the whole function. Maybe it's a whole mountain range. You want to find the top of the highest mountain. That's finding an absolute or global maximum. Or you could look for the bottom of the lowest valley, the global minimum. What else can we have for optimization? Well, we have this. We have here a mountain, z equals f of xy, similar to the last one. But instead of trying to find the very top of the mountain, we're going to say, suppose we have this trail map in the xy plane, and we're going to walk along this little trail down here. Can't make my cursor. There it is. Can you see it on there? It's hard to see even on the screen overhead. But suppose we're going to walk along this little trail down here, and subject to the constraint that we walk along the trail, what's the highest altitude we reach on the mountain, and what's the lowest trail we reach down below. So at the point x0, y0, we notice that on the trail, that's the lowest point we get to. And at the point x1, y1, that's the highest point we get to is z of x1, y1. So the constrained maximum, we say, is f of x1, y1. And the constrained minimum is f of x0, y0. And on this one, you can look at it and see it's going to have actually a constrained maximum and a constrained minimum, right? The reason being that you have a nice continuous curve down here and defined over it a continuous surface. So you're just moving along a continuous curve over this curve here. There will be a highest point with a single stroke of the pen and a lowest point with a single stroke of the pen. So this problem is kind of nice because in these kind of cases, we can guarantee both a max and min. That's not always the case. But that's what we're about today. What's the highest point on the mountain? What's the lowest point on the mountain? Subject to the constraint that we walk along the trail on our trail map. So here's the screen here. I'm having to go back and forth. Oops, just drew on it. Get used to the other program. All right, so walk along a trail map in the xy plane, subject to walking along the curve g of xy equals 0 is its equation. Ask what is the highest and lowest altitude on z equals f of xy. All right. Well, here's the one big theorem for today. There's only one theorem, really. Oops. It's called the Lagrange Multiplier theorem. And it says, suppose the surface there, z equals f of xy, is differentiable. And suppose the equation for the curve in the plane, g of xy equals 0, has g of xy a differentiable function. At any point where the gradient of g isn't 0, you can only have a maximum or minimum subject to the constraint at a point where there's a scalar lambda, is some number, such that the gradient of f is a multiple of the gradient of g. What that says is that the gradient to the surface level curves is parallel to the gradient to the constraint. So point in the same direction or opposite directions. And you can see why. There's a nice picture in the book that shows that. If I get a chance at the end, I'll show why this theorem holds just in an intuitive sort of sense without doing the whole proof. So that's it. All you have to do to solve the constrained problem is set gradient of f, the surface function, equal gradient lambda times gradient g. And you have to solve then for the points x, y that satisfy this equation subject to the constraint. Here's an example. Suppose I want to maximize or minimize, or both, the function f of x, y equals 4x squared plus 9y squared. And you can ask, what kind of surface is that, I wonder? We know what it is, right? If you rewrite it, as z equals x squared over a half squared plus y squared over a third squared, you realize that's an equation for an elliptic paraboloid, right? So we're trying to find what's the constrained maximum and minimum as we move along an elliptic paraboloid. And subject to a constraint xy equals 4 means we move, remember xy equals 4 is a hyperbola. You learned that from algebra. And so this is the picture here. I want to move along this hyperbola on my map in the xy plane. But I'm actually on the mountain up here. What's my lowest altitude I get and what's my highest altitude? This is what I really like about the picture. On the last one, we saw that there had to be an absolute maximum, constrained maximum and a constrained minimum. But here you can see there is no constrained maximum, right? Because you can go along this trail forever, unlike the ellipse in the last problem on your map, where you stayed in a confined continuous curve. Here, this goes out to infinity. Consequently, you can go higher and higher up the mountain here, up to infinity, and there is no highest point. So you know that when you solve the Lagrange multiplier problem, you can only find minima of this thing. So suppose we try to find the minimum altitude as we move along the elliptic paraboloid over this hyperbola, which has two branches here, right? X, y equals 4. It's just a curve y equals 4 over x, right? So it's the curve y equals 1 over x you love from algebra multiplied by 4. That's all it is. And so this picture then shows you that what you're looking for is the minima, not the maxima. Let's see. So what you have to do is write the one theorem that we have for these constrained maxima and minima, the Lagrange multiplier theorem, after the famous mathematician Lagrange. He was a student, I can't remember, Euler or somebody just after Euler, but he was down his line of mathematicians. And let's see, I've got to get both these computers set up here. There we go. There's the Lagrange multiplier equation. The surface equation that I'm trying to maximize, or in this case minimize, is f of x, y equals 4x squared plus 9y squared. The constraint curve I rewrite instead of xy equals 4 as xy minus 4 equals 0. And then I say that g of xy must be xy minus 4. The constraint has to be written as g of xy equals 0. So I'll do that by subtracting 4. Now, having written this as this Lagrange multiplier problem, minimize this function subject to this constraint, I take the gradient of the surface function, 4x squared plus 9y squared, and set it equal to multiplier lambda times the gradient of the constraint function, xy minus 4. So the gradient of f, right, I take the derivative of 4x squared plus 9y squared, I get 8x for the partial with respect to x, that multiplies I, plus partial of 4x squared plus 9y squared with respect to y is 18y, and so I've got 8x plus 8x I plus 18yj is the gradient of f. Is that one clear? I hope we just took the test. You should have all gotten your tests back, by the way. Everybody got their tests. If you didn't, let me know. The gradient of xy minus 4, partial with respect to x is y, and partial with respect to y is x, and so you've got yi plus xj, and that all multiplies lambda, the Lagrange multiplier. Now, if you think about it, two vectors are equal if and only if all their components are equal, right? So what we need is each I component to be equal. We need 8x on the left equal lambda y on the right, right? And wish I could reach there with my pointer. I should draw a laser or something. And then you need y components equal 18y multiplies j up there has to be equal to lambda x multiplying j on the other side. But if you think about it, that's actually only two equations in three unknowns, x, y, and lambda. So in general, I'm going to get an infinite number of solutions, and I'm not going to be able to sort through them to say which is the min. But I have one more thing, right? It also has to satisfy the constraint, xy minus 4 equals 0, or you can just write xy equals 4. So these three equations, the two we get from the Lagrange multiplier theorem, together with the constraint gives us three equations and three unknowns. Now, typically, once we have these three equations marked star here or asterisk, we can solve for a finite number of solutions in common practice, not always, of these three equations and three unknowns. So to solve this equation star, there's no set way. If it's a system of linear equations, maybe you take in linear algebra, you know it always has a solution, and you can always use Gaussian elimination or some other algorithm to find it. Not so on nonlinear equations. We said before, there's no set way. A common way is to substitute from one equation into another. So let's try that. In these first two equations, let's solve for where it says 8x equals lambda y. Let's solve for lambda, and we get lambda equals 8x over y. In the second equation, we got 18y equals lambda x. We solve for lambda, we get lambda equals 18y over x. Now, these two equations both are equal to lambda, so we set them equal. We get 8x over y equals 18y over x, right? Which then we can multiply through by xy. How can I be careful on this? When you multiply through by xy, you have assumed that x and y, the product xy isn't 0. We can assume this here because along the constrained path, xy equals 4, so it can never be equal to 0, right? But be careful before you multiply through, make sure you don't include the words. If you multiply through by xy, you've got 8x squared minus 18y squared equals 0. And now, if you think about that, that is an equation in just x and y. And the constraint is the one equation we haven't used yet is also an equation in x and y. So what we now do is we substitute from this equation we just found up here, 8x squared minus 18y squared equals 0. And the constraint equation in star up above, xy equals 4. And we have two equations and two unknowns. We can say in star, right, y equals, from xy equals 4, we write y equals 4 over x. I'm just looking for it, but there it is. And we plug that into the other equation involving just x and y. So what we did was we first substituted lambda out of the first two equations to get an equation x and y. Now we've got two equations both in x and y. We solve for y and one, substitute into the other. It's just algebra hocus pocus, whatever way you can think of. And now I have an equation 4x squared minus 9 times the quantity 4 over x squared equals 0 by substituting y equals 4 over x into 4x squared minus 9y squared equals 0. All right, so I've got this equation. Now this is an equation in x, so I just solve it. I multiply through x by x squared since x is never 0 along the constraint curve. And then I've got x to the 4th minus 36 equals 0. And I can solve that for x, right? I factor it since it's a difference of squares, right? That's x squared squared minus 6 squared. Factors, it's x squared plus 6, x squared minus 6, all equals 0. X squared plus 6 can't be equal to 0 because it's non-negative plus positive. So it must be x squared minus 6 equals 0. There's exactly two solutions for x, plus or minus square root 6, right? So those are the only possibilities for x based on the three equations and three unknowns. But that's not the solution, right? I now want to plug that in to my other equations to see what y has to be. If I plug it into the third equation, xy equals 4, it shows me that plus or minus square root 6 times y equals 4. Consequently, when x is plus or minus square root 6, right, y has to be plus or minus 4 over square root 6 or plus or minus 2 square root 6 over 3. which means that there's exactly 2 points. X can be plus square root 6, and y can be plus 2 square root 6 over 3, or y can be, x can be minus square root 6, and x can be that, and y can be minus 2 square root 6 over 3. So there's those 2 points, and what you do, you say, those are the only 2 candidates to get a minimum, a constrained minimum. So we plug them in and just see which one is smaller. Let's plug them in. Take f, the original function of both points. Right, was 4x squared plus 9y squared. I plug x and y in, and I got 48 for each of these, right? I plug in 48. All right, plug in and get, each of them comes down to 48. And so there's actually a minimum of 48, right? The maximum is out. And it occurs at 2 different points. Square root 6, 2 square root 6 over 3, and minus square root 6, minus 2 square root 6 over 3. And that's the answer then, minimum 48 at both those points. And here's the picture, if we can go to the next page. There it is. You've got a elliptic paraboloid. Z equals 4x squared plus 9y squared. And you're constrained to move along it over the hyperbola xy equals 4 in the xy plane. So the red curves up there show you where you can move, and sure enough, at both those points, minus root 6, minus 2 square root 6 over 3, and plus square root 6, plus 2 square root 6 over 3, we reach the bottom of the path along the elliptic paraboloid, the lowest point above the plane. So in this problem, there's no maximum because these curves going out to infinity, but there is a minimum at 2 different points. This illustrates some nice things about Lagrange multipliers. Any questions on that? You can come in online if you want to take the mic off for a second. I'd like to have you interact once in a while. Okay, so that's what we found. Now, let's try another one. This is kind of you'll see the material is getting more difficult. Huh? The good thing is there's only one theorem in this section. It's the Lagrange multiplier theorem. Find the point on the line now, 6x plus 5y equals 12, right? That's a general form of a line. Ax plus by equals c, with a and b not 0 is always a line, and every line can be put in that form. What's the point along that particular line, 6x plus 5y equals 12, that's closest to 0, 0, right? Lots of these problems in geometry, you'll see one in your homework for I think, maximizing the area of a rectangle that's inscribed in an ellipse, for instance. Whenever you see a maximization or minimization problem in geometry, maybe a Lagrange multipliers will work, right? It often does. So we want to minimize the distance from the origin. If you use the distance formula here, right, d equals square root x minus x0 squared plus y minus y0 squared, with x0, y0 the origin, you get that the distance from the origin is just square root x squared plus y squared there, right? You want to minimize d equals square root x squared plus y squared, subject to the constraint that you lie on the line, 6x plus 5y equals 12. You rewrite that. This is a common thing right here. Don't try and minimize d equals the square root. The square root is an increasing function, right? The square root of u, the larger u is, the larger the square root is. So instead of minimizing that square root and getting terrible partial derivatives, I'll instead minimize the square of the distance from the origin, x squared plus y squared. That makes the problem a lot easier. Do that on the homework. Don't minimize the square root, minimize the thing under the square root, and that will minimize the square root too. So we'll minimize x squared plus y squared, subject to the constraint, and we'll rewrite the line as g of xy equals 0. 6x plus 5y minus 12 equals 0. Now I can call the left side here g, the function to minimize f, and I have a Lagrange multiplier problem because both those functions are differentiable. Any questions on that one? All right. Here's the picture down on the next page. Oh, wait a minute. Hold on. There it is, down at the bottom. Okay, there we go. Again, to solve a constrained maximum minimization, this is what you have to do in the next test. Think, is this a local minimax? Is it an absolute minimax? Or is it a constrained minimax? In this case, we have a constraint that you have to satisfy that you lie along the line. So you try and you write down that problem and you set gradient of f equals lambda gradient g, the Lagrange multiplier equation, where lambda is an unknown multiplier. And the gradient of f, if f is x squared plus y squared, is just 2xi plus 2yj, right? Partial with respect to x is 2x, partial with respect to y is 2y, of the easier function x squared plus y squared that we're going to minimize. The gradient of the line, 6x plus 5y minus 12 equals 0, is 6i plus 5j, right? And so I have the gradient of f equals lambda gradient g is a multiple of the gradient of the constraint function. So now the components have to be equal. So 2xi must be equal to 6 lambda, right? The I component on each side are equal. So 2x equals 6 lambda. And the j component is equal. 2y has to be equal to 5 lambda. Again, that's 2 equations and 2 unknowns. What you want, ideally, is to get a finite number of points. You generally need to put in the constraint also. So we'll put 6x plus 5y equals 12. Now we have 3 equations and 3 unknowns. Chances are good that we'll be able to find only a finite number of solutions to that. It's not guaranteed, but typically. All right, so what do you have to do now? Again, you use by hook or by crook. You've got 3 generally nonlinear equations. These are actually linear equations. You could use matrix algebra on these in this particular case, but it might be easier just to substitute. For instance, in the first equation, if I divide by 2, I've got that x equals 3 lambda, right? Divide 2x equals 6 lambda by 2 and get x equals 3 lambda. Then I divide the second equation by 2 and I get y equals 5 halves lambda. Then I could substitute those into the third equation for the line 6x plus 5y equals 12 and get an equation in just lambda. 18 lambda plus 25 halves lambda equals 12. So that's writing x and y in terms of lambda in the first, from the first 2 equations, substituting them into the third. So it's generally a substitution method is what works on these. And now that equation, if you multiply by 2 to get rid of the fractions, you have 36 lambda plus 25 lambda equals 24. You can add those and get 61 lambda equals 24. Evidently lambda is 24 over 61. Try and guess that one, huh? Lambda we don't need. That's just an instrument, a tool to help us get to x and y. We're trying to find the point x, y that's closest to the origin. There's the picture, right? And you observe again, just by geometry, that there is no farthest point. You can keep going on the line forever. So any point we find that satisfies the Lagrange multiplier equation is a candidate for the minimum, not a candidate for the maximum. There is no maximum. Right? So we solve it. We have lambda equals 24 over 61. Well, x was 3 lambda and y was 5 halves lambda by the first 2 equations. So we just plug lambda in and we have x and y, right? It's 72 over 61 and 60 over 61. That'd be pretty hard to guess, right, on the test. So you need to solve this one. I might give you one just like this. This is a classic problem that's in most textbooks. There is the point that's closest to the origin, and you can plug in square root x squared plus y squared with those numbers to see what the closest distance is if you want. But you can see how you can derive a formula for the closest point to the origin. If you just wrote a generic line, ax plus by equals c, and did the same process, you can derive actually the closest point formula, which is kind of neat. Well, I'm going to take the screen share off, and I'll look at the board here simultaneously. So there's what we have. I want to switch over to the overhead here because my last 3 pages are on there. I think we have time for another problem here. Yeah. Here's a problem that's in the last one on your homework, and it's pretty difficult. We have there a function of 2 variables to maximize or minimize subject to a constraint. What if we have a function of 3 variables to maximize or minimize subject to a constraint? This is actually sort of a generalized problem, right? Now, because you're trying to minimize or maximize a function of 3 variables, you have to draw it in 4-dimensional space, right? W equals f of x, y, z. and subject to a constraint that's f of x, y, z equals c, 0, which is, or g of x, y, z equals 0, we usually write it, which is generally a surface in 3 space. So subject to the, you're moving around a surface in 3 space, minimize or maximize a function in 4 space of 3 variables, is a generalized problem. We can't draw it anymore, but we can still do it by the same technique. And here's a technique, here's an example problem. Find a tetrahedron. Tetrahedron is a 4-sided figure with triangular sides like this. This is the one in question. That lies on the first octant, right, where x, y, and z are all positive. Below the plane, x over a plus y over b plus z over c equals 1. So instead of writing ax plus by plus zz equals b, we'll write it in this form because it's convenient for the volume formula. Just to say a, you write 1 over a, but it's still an arbitrary non-zero constant. And if a, b, and c aren't 0, so that the plane sits out here like this in the first octant, it turns out there's a volume formula you can derive that the volume is ABC over 6, the book tells you. Right? So knowing that the volume of this is ABC over 6, let's try and find the tetrahedron where this plane, by the way, it intersects on A, B, and C. Do you see how to see that? These intersection points that you want to draw. Just like when you want to draw a line in the plane, you tend to find what's the y-intercept, what's the x-intercept. Similarly, when you find a plane in 3 space, put y and z equal to 0, and then you get x over a equals 1. You say, oh, x must be equal to a when y and z are 0. So the point a0, 0 is on the plane. Then you put x and z equals 0, and you say y over b equals 1. So y equals b is on the plane when x and z are 0. So that's the y-intercept. Put x and y equals 0, you get z equals c to get z over c equals 1. So it goes through the points a, b, c. See how easy it is? That's how you can actually sketch this easily. Now, on all planes that satisfy an equation of this sort, having intercepts a, b, c, suppose we want the plane that goes through 2, 2, 2, and what's the minimum volume that we can get? What plane has minimum volume if it runs through 2, 2, 2? Symmetry, you might be able to guess this one, but we're going to prove it, right? And you can make a harder one than this. This one is just supposed to be a little bit simple. So there's our tetrahedron. We think about it, we're trying to minimize the volume, which we said has formula ABC over 6, a function of 3 variables, subject to the constraint that 2 over a plus 2 over b plus 2 over c equals 1, right? That's the plane equation plugging in 2, 2, 2 for x, y, and z. So subject to the constraint that we go through 2, 2, 2 on the plane, we want to minimize the volume ABC over 6. And I'm going to make this suggestion once again, instead of minimizing ABC over 6, that'll be minimized when A times B times C is, right? When ABC is minimum, then ABC over 6 will be 2. So let's let f of ABC, the thing to minimize, be ABC, the product, and we'll simplify our algebra subject to this constraint, right? That 2 over A plus 2 over B plus 2 over C minus 1 equals 0. I'll rewrite it that way so I have 0 on the right-hand side. When I have a curve, the constraint curve as a function equals 0, then the left side can be called g of x, y, z, right? So I subtract 1 over, so I can say g of x, y, z equals 0 for the theorem. It has to be couched in that form. Minimize a function of 3 variables or maximize. Subject to a constraint, g of x, y, z equals 0. Here we're going to have the variables be a, b, c instead of x, y, z. Questions on that so far? I'm going to slide the page up here. All right. Now, we only have one tool. That's the good thing about this section. We just write down the Lagrange multiplier theorem. Gradient of f equals lambda gradient g whenever you see a constrained maximum or minimum problem on the test or on the homework. And gradient of f equals lambda gradient g with this f is ABC. Partial with respect to A is BC, right? Partial with respect to B is AC, and partial with respect to C is AB. So there is the gradient of f of ABC. It has to be equal to lambda times the gradient of g. Well, what's the gradient of g? The derivative of 2 over A is minus 2 over A squared, right? Plus 0 plus 0. If you take partial of this function with respect to b, then you've got 0 minus 2 over b squared and 0 plus 0. And if you take partial with respect to c, you get minus 2 over c squared plus 0 plus 0. And so here is the gradient of the constraint equation. That times lambda has to equal the gradient of the function to optimize. So now this time we have 3 component vectors that are multiples of each other, all right, since we've got 3 independent variables. Well, this can be very difficult because now what you've got is 4 equations in 4 unknowns, and that can be very difficult in practice. You have to keep these examples pretty simple. Because, right, there's lambda, a, b, and c. There's 4 variables. So we write down what this Lagrange multiplier equation says. It says that BC, the left side, is equal to minus lambda, 2 lambda over a squared on the right, for the x component, the first components. Second component is AC equals lambda times minus 2 over b squared. There that is. Equate third components to get AB equals minus 2 lambda over c squared. This is 3 equations and 4 unknowns. We need the constraint. 2 over a plus 2 over b plus 2 over c equals 1. 4 equations and 4 unknowns. Now, typically, we'll get only a finite number of solutions. We can plug them in to check them, right? How can we solve these 4 equations and 4 unknowns? When I looked at this at first, I just flustered and realized here's the easy way to do it. Multiply this first equation through by a and get ABC equals minus 2 lambda over a. Multiply the second one by b and get this. Multiply the third by c and get this. How did I know to do this? I just flustered for a while. There is no standard technique. Usually you use substitution of some sort. And what I'm thinking is if I get these all a, b, c on the left, then I can set them equal. So that's my strategy on this. ABC is equal to this, this, and this. Therefore, these 3 things must all be equal. Minus 2 lambda over A must be minus 2 lambda over B must be minus 2 lambda over C. And we also have the constraint, 2 over A plus 2 over B plus 2 over C equals 1. Right? 4 equations and 4 unknowns. Now, if these, by setting all 3 of these things, let's see. Since these things are all equal, we have right sides equal, right? And now we recognize by dividing by minus 2 lambda that A has to be equal to B, B is equal to C, right? And if you divide by minus 2 lambda, you just get 1 over A is 1 over B is 1 over C. A, B, and C have to all be equal. So there's a big hint. Now we can plug A equals B equals C into the constraint equation and get 2 over A plus 2 over A plus 2 over A, since B and C are both equal to A. All has to add up to 1. And finally, we've got 6 over A. Adding these numerators over the common denominator has to equal 1. Evidently, A equals 6. There it is. But A equals B equals C, so that means B and C are 6. All right? And there's only one solution plane. It's A, B, C all equals 6. X over 6 plus Y over 6 plus Z over 6 equals 1. What's there's a question on that one? Anybody? Don't have my question answers together today. All right, so they're pretty tricky. See, there's a lot of different situations that come up and lots of different algebra to try and solve these multiple equations and multiple variables. But the idea is to get the same number of equations as unknown between the Lagrange multiplier equation and the constraint. We'll make some notes then as follow up to this. Sometimes you might have a function to be maximized, a function of 3 variables like we just had, subject to 2 constraints. If you have at least 3 variables, you can have more than one constraint for the following reason. We might want to maximize this function of 3 variables in 4-dimensional space, right? W equals all this. Subject to lying on this surface in 3-dimensional space and this surface in 3-dimensional space. So we're taking the intersection of these 2 surfaces might be some curve, and thinking about moving along the curve that's the intersection of these surfaces in 3-dimensional space. What's the maximum of this function of 3 variables in 4-dimensional space? You know, what's the maximum W you can generate? You know, so it's pretty complicated geometrically, and you can't draw it anymore. But the Lagrange multiplier theorem is the same. If these are all differentiable, the Lagrange multiplier theorem now becomes this with 2 constraints. You just simply write, I think one of the homework problems has this on it, actually. Gradient of f equals lambda gradient g plus mu gradient h. So instead of writing gradient of f as a multiple of gradient g, it's multiple of gradient g plus a multiple of gradient h. where G and H are the constraint, the left side of the constraint equations. And now what you have, you call lambda and mu, these are both Greek letters, the Lagrange multipliers, both of them. And what you get is 5 equations and 5 unknowns. 3 of them from equating these vectors that have 3 components. And then 2 constraints, G equals 0 and H equals 0. 5 equations and 5 unknowns. I don't think have time today to do one of those examples. But if you're asked on the homework that, and I think you are, that's what you do. You get 5 equations, 5 unknowns, and you know, in the book there'll be simple equations to solve. But you can have more than 2 constraint equations when you have at least 3-dimensional functions of 3 variables. All right, and all you have to do is find those things that satisfy the Lagrange multiplier equations, the 2 constraints, and plug them all in to see which is biggest and which is maximum, which is smallest, provided there's a finite number of them. All right, and then this is just a reminder of the first one. I guess I don't need that here. See how I'm going for time. I think I've got, yeah. One comment then on the theorem. Geometrically, the theorem looks like this. Here's its concept. And we'll only do it for functions of 2 variables, but we just can't draw it higher dimensions. We're trying to draw it. So we'll say for z equals f of x, y, subject to g of x, y equals 0, find the constrained max or min the idea is that you can look at level curves of f for different values of k. So maybe you get something like this. Maybe this is k equals 0, k equals 1, k equals 2. These are level curves of z equals f of x, y. Plot on the xy plane. Remember, these are the traces by cutting it with horizontal planes, then projected down under the xy plane to make a contour plot. And then g of xy equals 0 is some other constraint curves as you're moving along. Maybe it's this one. And the idea is that where are you going to maximize or minimize g? And here's another maybe level curve of f. Well, think of these as isopleths of a mountain, right? This is a higher altitude, this is a higher altitude. You know that the gradient of f is perpendicular to the level curve of f. So if these are level curves, then it has to point perpendicular like that. Right? So this might be gradient of f. But g of xy equals 0 is actually a level curve of the function z equals g of xy. So its gradient is also perpendicular to this constraint curve here. Now, if they're both perpendicular to these curves, now where you reach the highest point along g ought to be tangent to a level curve here, right? You just get up to this highest level of a mountain right here, and then you start back down. The idea is you want to find a maximum when you're tangent to one of the isopleths, and also the minimum. Right? These are getting smaller and smaller isopleths as you go down on these level curves of f. And so what happens is where you find the maximum altitude, the gradients are going to be parallel to each other. That means they could be the same direction or opposite like I've drawn, but they're both perpendicular to their level curves of f and g. And the concept of the theorem is they therefore are multiples of each other. Similarly over here, where there's the minimum, so this might be the minimum altitude on the mountain. Oops, goes the other way, sorry. Remember, the gradient points in the direction of increasing value of the function. These are higher levels on the mountain up here. And then g of xy might have its gradient the same direction or the opposite. Let's say it goes like that. So there's gradient g is also perpendicular to the gradient of f at the lowest altitude. But that's the idea. This is what you just tangent to the one at isoplex when you're at the lowest altitude, just tangent to the one at isoplex when you're at the highest altitude. And so that idea of both being tangent means their gradients, which are perpendicular to those, have to be along the same line. So that's where the theorem comes from. I think the intuition on that theorem is actually better than writing the formal proof. Any questions for today then? That ought about do it. Go ahead and try those problems and see if you have any questions. Send me emails or bring them beginning next time. Thank you for coming out in the cold today.